String theory is one of the most compelling and ambitious theoretical frameworks in modern physics. Its primary goal is to provide a unified description of all fundamental forces of nature, potentially reconciling the currently incompatible theories of quantum mechanics and general relativity. String theory suggests that the most fundamental constituents of the universe are not point particles, but rather tiny, vibrating strings. These strings can be open or closed, and their vibrational modes determine the properties of the particles they represent, such as mass and charge. Historical background. The origins of string theory can be traced back to the late 1960s, when physicists were attempting to understand the strong nuclear force, which binds protons and neutrons together in the nucleus. In 1968, Gabriele Veneziano discovered a mathematical model that described the scattering amplitudes of strongly interacting particles, which led to the development of the Veneziano amplitude. Soon after, Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind independently realized that these scattering amplitudes could be explained if the particles were actually one-dimensional objects, or strings, rather than point particles. Throughout the 1970s and 1980s, string theory evolved rapidly. Initially, it was proposed as a theory of hadrons, particles composed of quarks, such as protons and neutrons. However, it became apparent that string theory had broader implications, and it was reinterpreted as a potential theory of everything. This shift was catalyzed by the realization that string theory inherently includes gravity, as one of the vibrational modes of a string corresponds to the graviton, the hypothetical quantum particle that mediates the gravitational force. Basic concepts of string theory. Strings and vibrational modes. The fundamental idea of string theory is that the basic constituents of the universe are not zero-dimensional point particles, but one-dimensional strings. These strings can vibrate at different frequencies, and each vibrational mode corresponds to a different particle. For example, the electron, quark, and photon can all be seen as different vibrational states of the same type of string. Types of strings. There are two main types of strings in string theory: open strings and closed strings. Open strings have two endpoints, while closed strings are loops with no endpoints. These different configurations lead to different types of particles and interactions. Supersymmetry. Many versions of string theory incorporate the concept of supersymmetry, which posits that every fundamental particle has a superpartner with different spin characteristics. Supersymmetry helps to stabilize string theory calculations, and potentially explains why particles have the masses they do. Extra dimensions. String theory requires the existence of additional spatial dimensions beyond the familiar three. The most common version of string theory, known as superstring theory, requires 10 dimensions, 9 spatial dimensions, and 1 time dimension. These extra dimensions are thought to be compactified or curled up so small that they are not observable at human scales. Branes. In addition to strings, string theory also predicts the existence of higher dimensional objects called branes, short for membranes. Branes can have various dimensions, from zero-dimensional points, 0 branes, to 9-dimensional objects, 9 branes. Our universe could be a 3-brane, with strings attached to it, which would explain why we perceive only 3 spatial dimensions. 5 superstring theories and M theory. Initially, 5 consistent superstring theories were discovered. Type 1 string theory incorporates both open and closed strings and features a unique form of symmetry known as SO32. Type IIA and IIB string theories. Both involve only closed strings but differ in their chirality. Type IIA is non-chiral, whereas type IIB is chiral. Heterotic SO32 and heterotic E8xE8 string theories. These theories combine aspects of bosonic string theory and superstring theory, resulting in closed strings with additional symmetries. In the mid-1990s, the understanding of these theories underwent a profound transformation with the advent of duality symmetries. Dualities are mathematical transformations that show the equivalence between seemingly different theories. These discoveries led to the unification of the 5 superstring theories into a single framework known as M-theory, which is believed to be a fundamental 11-dimensional theory encompassing all 5 superstring theories. The exact nature of M-theory is still not fully understood, but it is thought to include membranes, two-branes, and other higher-dimensional objects in addition to strings. D-branes and non-perturbative effects. One of the significant advances in string theory was the discovery of D-branes, a type of brane that can have open strings ending on them. D-branes play a crucial role in non-perturbative aspects of string theory, which are essential for understanding phenomena that cannot be described by simple perturbative expansions. The study of D-branes has led to deep insights into black hole physics, gauge theories, and the holographic principle. The holographic principle and ADS-CFT correspondence. The holographic principle is a conjecture suggesting that the description of a volume of space can be encoded on its boundary. This idea gained substantial support from the ADS-CFT correspondence, formulated by Juan Maldacena in 1997. The ADS-CFT correspondence posits a relationship between a type of string theory defined in a higher-dimensional, anti-de Sitter (ADS) space, and a conformal field theory (CFT), defined on the boundary of this space. This duality has provided powerful tools for studying quantum gravity and strongly coupled quantum field theories. String theory and cosmology. String theory has profound implications for cosmology. One of the most intriguing is the idea of a multiverse, where our universe is just one of many possible universes with different physical laws. String theory also offers potential explanations for the initial conditions of the universe, the nature of dark matter and dark energy, and the resolution of cosmological singularities, such as the Big Bang. Challenges and criticisms. Despite its elegance and potential, string theory faces several challenges and criticisms. Lack of experimental evidence. To date, there is no direct experimental evidence for the existence of strings or extra dimensions. This has led some physicists to question the empirical testability of string theory. Landscape problem. String theory predicts a vast number of possible vacuum states, each corresponding to a different set of physical laws. This landscape of solutions makes it difficult to make precise predictions about our universe. Mathematical complexity. The mathematical framework of string theory is highly complex, and many aspects of the theory remain poorly understood or speculative. Recent developments and future directions. Research in string theory continues to advance, with several promising directions. String phenomenology. Efforts to connect string theory with observable physics, such as particle physics and cosmology, are ongoing. This includes finding ways to derive the standard model of particle physics from string theory and making predictions that could be tested by experiments like those conducted at the Large Hadron Collider, LHC. Quantum gravity. String theory remains one of the leading candidates for a quantum theory of gravity. Progress in understanding black holes, spacetime singularities, and the nature of spacetime itself is being made using string theoretic techniques. The mathematical insights. String theory has led to numerous breakthroughs in pure mathematics, including the understanding of Calabi-Yau manifolds, mirror symmetry, and knot theory. These mathematical insights have applications beyond physics, contributing to fields such as algebraic geometry and topology. Conclusion. String theory represents one of the most ambitious and far-reaching endeavors in theoretical physics. While it has not yet provided definitive answers to all the fundamental questions of nature, it has profoundly influenced our understanding of the universe's underlying structure. Its mathematical beauty and potential for unification make it a compelling area of research, promising to yield new insights into the fabric of reality. Whether string theory will ultimately be proven correct remains an open question, but its contributions to both physics and mathematics ensure its place as a cornerstone of modern theoretical science. Thank you for watching. Please subscribe our channel.